Introduction to gases. So gas chemistry is essential to understand because when I have a chemical reaction, right, a chemical reaction between anything, let's say I have a chemical reaction between A and B, all right? If A and B are going to come together and do some chemistry, now they have to hit each other. They have to actually be in enough proximity for them to collide, and then they decide what they want to do. Do they one want to give electrons to others? Do they want to share electrons? Whatever it is. But they have to be in close proximity, and they have to actually collide together. All right? If A is some pile of material and B is some liquid, right? So maybe this is a solid and this is a liquid. Then if I pour the solid into here and it makes a big pile of stuff on the bottom, there's not going to be very much chemistry that can occur because the relative amount of atoms from A, which are available to B, are going to be limited. All right? And if it was a different scenario where we had two different compounds, E and D, both of these, let's say they're solid, and we want them to come together to form a new compound, all right? If these are both solid, that's going to be an extremely unreactive process, right? Because mixing two solids and trying to combine them, we might feel like, oh, I'm mixing it up really good, but the chemistry is just not going to occur. It can't occur unless something is in a phase, like a gas phase, where all the atoms are separate from each other. In the past, in Chem 105, all of our reactions, like if we were combining sodium chloride, here's a good review. Who's up? Aisha. This is a tough one. Good review. Sodium chloride mixing with silver nitrate. What are the products for that reaction, Aisha? Do you know?
Silver chloride and sodium nitrate.
Very good. Silver chloride and sodium nitrate. All right. The way that this happened, the way that this chemistry could occur, is because these, what were the phases on these ones? Do you remember, Aisha?
They're both aqueous.
That's right. They have to be aqueous. And in an aqueous scenario, then yeah, you can get some chemistry to occur because all of the ions are all separated and floating around. All right? So unless you have either aqueous or something in gaseous phases, then the chemistry is going to be significantly limited. So understanding how gases kind of react and behave is a critical component to understanding how chemical reactions can proceed. So gases, right, they take whatever shape you put them into, right? If I put them into a container that's shaped like a sphere, they'll take up that shape of that sphere. If it's shaped like a cube, they'll fill in all the corners and spread out as far as they can, right? They're less dense than liquids, right? Bubbles always rise up out of liquids, right? We know that hot air balloons rise, so the hotter a gas, the less dense that gas becomes, okay? So these are some properties of gases that we already know. When we talk about gases, what they're doing at an atomic level, what we want to envision and what works is they're individual atoms zooming around whatever container they are, bouncing into the edges of the walls or the sides of the walls. In a balloon, the reason a balloon holds its shape, we can say, this is a little reflection to make you see it's a balloon. Isn't that pretty good? So we have little balls of whatever gas is in here floating around, bombarding the inside of the balloon, keeping the shape the way it is. All right. So we can heat up this balloon and the balloon will expand. We can cool it down and the balloon will shrink in size, right? I don't know if you guys have ever taken a balloon and put it in a really cold condition. You need to get something like liquid nitrogen. But if you take a balloon and put it into liquid nitrogen, it'll essentially form a flat balloon, right? It'll just be a flat balloon because the volume of the gas in here, when it's converted to a liquid, and that's what we do when we cool something down, right? We call it going from a gas to a liquid. We call it condensation. Condensation results in a material with a much smaller volume. And that's another reason why gases are always much less dense than either liquids or solids. Okay? Pressure. Pressure is basically the collective measurement of how much force is being exerted by the gas molecules on either the inside of the balloon, on some surface. Like if I have gas pressing down on a container of mercury, this is supposed to be a container of mercury in a tube, that mercury will be forced up as the gas pressure pushes down. Why do we use mercury? Because it's a liquid and it's very stable, dense, and so it won't evaporate away, it won't fly away, right? Now, units for units for pressure. We haven't ever talked about pressure, so these are all new units, but millimeters of mercury is actually a unit of pressure. Now, we use millimeters of mercury because, again, it's easy to think about. For example, I have a tube here, right? It's in some sort of a container. Inside the container, I have some mercury. The tube is pushed into the mercury, right? And if I have some sort of a seal here, maybe it's a flexible seal, and then I increase the pressure, then that will push down the mercury here, and the mercury there will rise up because there's less pressure in this region in here. Or vice versa, if I have a lower pressure outside, then the pressure inside can push this mercury down. And the resulting difference between, let's look at this up close now. If I have my column of mercury, inside the tube and outside the tube, all right, so this is again a container here. It's filled to the top with mercury, so there's my level of mercury. As I put pressure on this, this mercury rises, this mercury lowers, and the result is a difference in the level of mercury. And that difference is going to be measured in centimeters or millimeters, and it will be one way to measure how much pressure has been exerted on the mercury surface itself. So 1 unit for mercury is what we call millimeters of mercury, or torr. Torr is another way to say millimeters of mercury, all right, named after a famous or a scientist who worked on it, Torresini. I think that's his name. There it is, Torricelli. Evangelista Torricelli. So, units of pressure, millimeters of mercury, or torr, there it is, 1 millimeter is 1 torr. Atmospheres of pressure, all right, just another unit to describe pressure of gas. And 1 atmosphere is 760 millimeters of mercury, or the same as 760 millimeters of torr, okay? So these are our pressures, our units that we'll be using for pressure, okay? And just like before, if we know what units we want to have, so if somebody says, how many atmospheres are there in 675 millimeters of mercury, we can use Google to find out what the conversion factor is here, and then we can use that conversion factor to identify the answer in terms of either atmospheres or millimeters of mercury, all right, or torr. Okay, very good. So, when we're at the bottom of the ocean, we are under an increased amount of pressure. Has anybody had that chance to go scuba diving before? If you want to say yes on the right chat button there, if you've had a chance to go scuba diving. But when you go scuba diving, there's some precautions you need to take when you go to very deep depths. Robert, do you want to describe to us the precautions that you need to take when you go down deep in scuba gear?
Right. So when you're in the scuba, or when you're rising, I guess you could say you can't rise to the surface too quickly, but that you have to make sure the oxygen in your tank gives you ample time to rise to the surface without rising too quickly.
All right. And Chad, do you remember what the threat is? Why is it that you can't rise too quickly? What's the problem there? Do you remember, Chad?
The problem is that you get, I forgot exactly, I think it's nitrogen. You get too much nitrogen in your body, and that can cause a variety of symptoms, but makes you have misleading judgment, and it's just overall dangerous.
Okay. So, I bought some fish the other day. Unfortunately, I bought one male and 3 females, and I wanted them to reproduce, and the male died, and now one of the females died. And this is my fish tank here that I have, all right? I have water in my fish tank. Here is one of my fish, right? Do fish breathe? Do they need oxygen? What do you think? Write it in the column there. Do fish need oxygen? Yes, of course they need oxygen. Where do they get that oxygen from? Where do they get the oxygen from? They get the oxygen that is dissolved in the water. The oxygen that's actually dissolved in the water. So there are oxygen molecules that are actually dissolved in water. And you can increase the oxygen molecules that are dissolved in water by bubbling, right? Bubbling oxygen. So bloop, 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 bubbles of oxygen go through. And as they go through, a little bit of that oxygen dissolves in the water. All right. So the oxygen needs to be dissolved or is in the water, and the fish can absorb that oxygen. So we have a gas, O2 gas, dissolving into that water. Now I can increase the amount of gas, oxygen, nitrogen, whatever it is, that will dissolve in that water a couple of ways. I can cool down the water. If you cool down the water, then more oxygen will be able to be dissolved in it. I can also just kind of push it in, right? So if I had some sort of a container here with a liquid, let's say that's my water there. And then let's say I took some sort of a plunger apparatus, right? And just pushed down hard and tried to squeeze this gas into that water, right? That's a possibility. I can dissolve more gas. This is the gas. If it's air, you know, what's in air? Do you guys know what's in air? What is the gas that we're always breathing? Give me some answers in the chat down there. What are some of the gases that are in the air that I'm breathing? Oh, I can feel it. I think I know what it is. I can tell. Oxygen, that's one of the things. Oxygen about 20%. Nitrogen about 80%. So about 80% nitrogen. And then there's trace amounts of carbon dioxide, a little bit of carbon dioxide, and trace amounts of argon. Trace amounts of argon gas. And if you're unfortunate and you're in a basement somewhere in Utah, you might find some radon that actually gathers down in low spaces, which is toxic and will kill you because it's not oxygen, right? But we can increase the amount of those gases that we dissolve in any liquid by pushing more pressure on the surface of those gases and making them dissolve into there. So because we know now that you can increase the amount of gas that dissolves into a liquid, when you're underneath the water, the pressure of the ocean that's above you, or the water that's above you, the pressure of that water will force more of the air that you breathe in your scuba device into the blood and tissue that it's being delivered to. And that's why we breathe, right? We are breathing in oxygen to get that oxygen delivered to our body. Our body needs to incorporate that oxygen into us, and that's a good thing. However, if you have a certain amount of oxygen and nitrogen dissolved in your blood and in your tissue, now why is it dissolved? Because that's what it does when you breathe it in. And why is more of it dissolved when you're at the bottom of the ocean, Alyssa? Why is more oxygen dissolved in your body when you're at the bottom of the ocean?
Because the density is so much greater, so you're inhaling it at a greater rate because the pressure.
The pressure, that's right. The pressure of all of the atmosphere above you is pushing more of that into you. So then if you have a certain amount dissolved in your blood and tissue, and then you try to zoom up really fast without breathing in and out, then that gas will try to come out of your blood and tissue wherever it's at, as opposed to being allowed to come out by just breathing in and out, right? It'll begin to come out anywhere it can, and those little forms of bubbles will do lots of damage to your tissue, wherever it is. If it's in your heart and your heart gets damaged, you'll die. If it's in your lungs and your lungs get damaged and you can't breathe, you'll die, right? It doesn't take much to shut down just a few organs in your body and you'll die, right? So that's why the bends, is what it's called, is very, can be very damaging. And it's also a reason why, do you remember, who was it? Robert and Chad, was it? Saying they had been scuba diving. What is a precaution you need to take for the first couple of days after you're done scuba diving? Do you remember that? Either of you? What is the precaution you need to take after you're done scuba diving? You're not supposed to do something for about 2 days.
You're not supposed to dive again.
You're not supposed to dive again? Okay. There's another one that I am aware of. You're not supposed to go flying in an airplane. Now, why do you think that might be a problem, Chad? Why is that a problem, based on our discussion?
From what my understanding is, when you're down low and you're under pressure, think of your lungs like a balloon. And when you're low, your lungs shrink. And so, like, if you rise too fast, the oxygen's going to leave, or is going to overinflate your lungs. And so I assume if you go from really low altitude to really high altitude, it might have the same effect. Also, like taking a soda can or a water bottle from, the airport into the air, it just changes the surface area of the bottle, just like your lungs.
That's right. Okay, so one last thing before we go. Here is the ocean. Here's a person, right? We said that when a person goes to the bottom of the ocean, they have a lot of pressure on them because of all of this weight of the water. Well, this person doesn't know it because they're not used to thinking of it this way, but they are also at the bottom of the ocean. Not an ocean of water, but they're at the bottom of the ocean of this atmosphere, right? And so when you come up to the top of the ocean, out of the surface, right? Up here we'll say is space where there's no atmosphere, right? Then you also have a significant change in the amount of pressure that's on you, all right? So we're going to talk more about that, how this atmosphere actually is imposing on us all the time a significant amount of pressure on our body and also on our chemical reaction that we might be performing in the lab, right? The pressure of the atmosphere is always putting pressure on everything around us. Okay, very good.